Section 5.6 is called field speed control. And what that means is exactly what it says. We're going to control the speed by altering the field. And of course, when we're talking about the field, we're talking about the magnetic field. And we can alter that magnetic field by changing the excitation current that is supplied to the field. And so we'll look at this wide range of options that this type of speed control gives us. We'll even look at being able to take a DC motor and cause it to go well beyond its rated speed. So we'll incorporate, all our prior knowledge and our equations that we've developed up this so far. And we'll begin with equation 5.7 and walk through this a little bit and take it up a notch. Okay, so Wilde begins this section. He says, according to equation 5.7. So let's make sure that we know what equation 5.7 is. We went to a lot of work and you suffered through a lot of videos to get to the point to where we were able to develop this equation 5.7 that says that the speed is equal to 60 times E sub S divided by Z times the field pole flux. Okay, so that's what we're going to explore, and that's what we're going to look at altering, so that ultimately the idea here is to change the speed. Changing the speed of a motor is a big deal, and there's a lot of control systems that go to lots of different schemes as to be able to do that. And initially, again, the primary advantage of the DC motor was the fact that varying the voltage, there was this direct relationship between a voltage change and the speed of a motor. Okay, and so as we get further into this, and you probably don't see that right now, the idea that we can do this with this AC motor that we in this class with, it's pretty remarkable, and it's really an important thing that allows motors to be such a part of everything that we do, electric motors. So anyway, he says, with this equation 5.7, he says we're going to keep this this source voltage steady, and so keeping the source voltage steady, and knowing that the number of conductors we can't change once the motor is designed and built. So really, what are our options? Our option is to change the field. So motor speed changes in inverse proportion, according to this equation, to the size of the magnetic field. So if you increase the flux, if this number here goes up, then that's going to go down. If this goes down, this will go up. So anyway, that's what we're looking at here with this equation, and how we're going to manipulate things so that we can take advantage of it. Now, this method of speed control is frequently used when we need a motor that can actually run above its rated speed. And there are instances where we want to do that. But if you think about it, as this flux number gets smaller and smaller and smaller, this speed gets very large. And, mathematically, there's no limit to what the speed would be, right? And we'll explore that part of it too. But there is a range within the design of the motor that makes that, undoable. So, it's theoretically you could do that, but we'll see what actually happens with a motor. Okay, and so what we're going to do, and I like this is sort of our first one of these. Here is the motor schematic that we're looking at. And what we like to do in electrical machines is we like to model certain types of electrical machines so that they fit varying voltages. And so we always have these characteristic curves that go along with a particular motor. And this is this motor, here's the armature of the motor, here's the shunt field that's in parallel with the armature, here's the armature resistance right here, and then here's the source voltage, E sub S, that is supplied. And as we can see, the current is going to the armature. So the motor, of course, is acting as a motor. It's absorbing power to it. And then what we can do is we can vary this field rheostat across here. You know, this would be this would be maximum resistance, and here this would be minimum. Excuse me, I've got that just the opposite. This would be minimum resistance here, and this would be maximum resistance here. And by changing that resistance, we can change the I sub X, or the excitation current. And then, you know, according to the equations that we've all worked through, changing that excitation current, increasing the flux, changes the output voltage, right? So we got all that going on. But anyway, initially, you know, this counter EMF, counter electromotive force, right now it's slightly less than the supply voltage, and that's due to this drop in voltage that occurs here, right? So E sub S is greater than E sub O by a small amount. And then he says, what if we suddenly increase the resistance of the rheostat? What if we suddenly increase the resistance of the rheostat by moving it down in this direction? Then both the excitation current will diminish and also the flux will diminish, okay? This immediately causes this number to go smaller, the armature voltage. If the armature voltage goes smaller, then the current, you know, this E sub S minus E sub O divided by this resistance, if this number gets a lot smaller, then this current is going to go way up, right? So immediately what happens is, you know, that goes down, current goes up. And so the motor will respond by accelerating because because of the situation that's gone down, okay? Now, he says the current changes dramatically because its value depends upon the small difference between source voltage and armature voltage. So despite the weaker field, the motor develops a greater torque, and it's going to accelerate until this E sub O gets back to the state that it was prior, to where it's close to E sub S, okay? So there's this interaction that's going on between these two voltages. Now, to be able to do that, the motor has to turn faster. Everything else is, you know, equal. The only way you can do that is for the motor to accelerate. So we can even raise the motor speed above its nominal value by, you know, introducing this resistor in series with the field. But for shunt wound motors, shunt wound parallel, this method of speed control enables these high speed base speeds ratios, and you can actually have this ratio up to 3-to-1 in terms of the base speed and this high speed, you know, and strictly it's done by the varying of the flux that we could do by using a field rheostat in the circuit. And now beyond this 3-to-1, he tells us that physically there are problems with stability and commutation within the motor, and so it's you know, it's difficult to go beyond that 3-to-1 ratio. Now there is a certain thing, and I'll try to demonstrate this in the lab to you, that under abnormal conditions the flux may drop out. You know, for example, maybe the excitation of current of a motor is interrupted accidentally, and the only flux that would be left would be this remnant magnetism in the poles. that flux becomes so small that the motor has to rotate at these dangerously high speeds to induce this required counter electromotive force. And under those conditions, we call those conditions where this were to drop to very low levels a runaway condition. That's something that we have to try to avoid with a DC motor, and we'll put things in place in our control system to make sure that that doesn't happen. Okay, that's enough out of 5-6, and we'll terminate this, and we'll take this same motor in the next section, and we're going to put a load on it and watch what happens.